Now, another mystery. I'm going to start with one of my favorite indicators. Doesn't take much. In fact, it's like I can almost wave this container in front of this flask to get enough of this indicator. Congo Red. In the 1880s, 1890s, they found out that you could take coal tar and make dyes out of it. And they just went whole hog making all these beautiful dyes. If you lived around 1820, 1840, 1850, it'd be pretty drab. There weren't a lot of bright colors, and it was very difficult to get dyes that had color in them. In fact, the big industry was making indigo, and because it was a beautiful purple, but they found out how to make these dyes artificially using tar, and they came up with hundreds of these, phenolphthalein one of them. They even found out that a lot of these dyes had antiseptic properties. But that's another story, another time. And I'm going to right now, there's water in there. Congo Red is a pretty orangish red in a neutral solution, even if it's slightly basic. I've got these little pieces of, let me get a clear beaker. I held it in my hand, so you know it's not too dangerous. Let me hold this up here. This stuff conducts at room temperature. It would conduct if I melted it. So, and it's an element. So, what type of element? Pardon?
What is the stuff in the little beaker?
Yeah.
What is it though?
Pardon?
What is it?
That's my question to you.
Oh, okay.
So this keeps you involved. It keeps you watching. It conducts electricity as a solid, and also if I melt it, it would conduct electricity. So what classification?
Metal of some sort.
Yes? Metal or non-metal?
A metal.
Oh, it's a metal. It doesn't look like it because it's corroded a bit. It's got that white powder because it rusted. It combined with oxygen to make a white powder. I'm dumping it into water. And we're going to give it a couple of minutes. Can you, let's see, give it a couple of seconds. Your reaction is pretty slow, but I'm starting to get some fizzing. And let me fill this up again. There's my water. Whoa, it's fizzing and fizzing. It's starting to react faster and faster. This is an exothermic reaction. And as it heats up, it produces more heat, which makes the reaction go faster, which makes the reaction go faster. It's a runaway reaction. One of the problems with exothermic reactions is once they start going, they increase their rate because they produce heat that increases the rate of their reaction. So, okay, oops, let's get this in here again. Okay, I've got it in there. Let's collect this gas by water displacement. Again. Oh, we're getting it. Look at that. That's a rate of reaction. So we're going to try and identify this. Whoa, it's steaming. It's boiling hot right now. And I've collected the gas. And it's still going. Look at that. Beautiful, beautiful pink. Now, again, one of the classic ways of testing for gases was the splint test. In this case, I'm going to use a burning splint. This will help us identify that metal. I get my burning splint going, and now I'm going to get my graduate cylinder with that produced gas. I'm going to ask you what it is by, whoa! Look, there's condensation all along the inside of this graduate cylinder.
I'm going to make a wild guess that is oxygen.
No, the splint would have just.
Is it hydrogen? Because that's how hydrogen explodes.
You're right. That was a hydrogen explosion. That was hydrogen. Oh, it's all gone. It escaped. The reaction has completed. So we generated hydrogen, and there are a lot of metals that react with water to make hydrogen. That's pretty common. The metal 0, it tends to lose electrons to become a cation. And if you've got water gaining electrons, the H plus in the water becomes H0. The water going from +1 to 0 is reduced to hydrogen gas. And the oxygen that combined with it is oxidized. But this reacted pretty quickly. So any ideas of what two families of metals react with water quickly?
Alkali and alkali earth.
Yes, alkali metals and alkaline earth. This one produced a +2 charge.
So it's alkali earth.
Alkali earth. And in this case, if it's an alkaline earth, we're talking about magnesium, calcium. Barium is a bit expensive. Magnesium, if you toss it into water, it doesn't react that quickly. The water's got to be steaming hot. In this case, it was calcium. The calcium ended up making calcium hydroxide, which is the precipitate that we've got in here. It's a white precipitate. My Congo Red is in there right now, and I can put my safety glasses on. By the way, when you get in college, buy a good pair of safety glasses. Don't buy a cheap pair. Because then you won't wear a cheap pair. They're uncomfortable. A good pair of safety glasses, won't cost any more than $10, and you'll be wearing them a lot. But I've got my safety glasses on, is because here's some 6 molar hydrochloric acid.
Mr. Moskalik, with this,
Yes.
you can work with beryllium too.
Oh, yes. Beryllium, you don't want to work with because it's so toxic. Beryllium is acid, turns Congo Red blue. A little bit more acid. Now we're talking about equilibrium. The solution is acidic, but as it reacts with the calcium hydroxide base, it may turn back into a base. In fact, let me toss some more calcium in. Here's my calcium. You very rarely will find calcium that looks shiny because it oxidizes so much. And I've tossed it in there. And now that we have hydrogen ions, it's probably going to react even faster. Let me toss a bit more in. And we'll see if I add enough to neutralize the hydrochloric acid. Oh, look, we're going to get some pink on the top. But then the acid dumps its protons onto the Congo Red to turn it into its... Oh, it's getting hotter now. Okay, it's getting hotter. So we've got our pink, and then when it gets acid again, we've got our blue. So, and we're making hydrogen on top of it all. Yeah, again, shop for some good safety glasses. Don't use the standard ones that they have. Oh, it's about to overflow. It's getting that hot right now. I could add some more acid in there, and it would turn blue, back and forth in equilibrium. Okay, we can watch it foam over, and now you'll know that it's there. And I'm going to flip over to me. Okay, one quick story. One of my favorites, I read a science fiction story of some people on a planet, and there were these reptiles that they were fighting. The reptiles had amazingly fast powers, and they couldn't figure out how they could be that quick. Because, I mean, when you run a lot, you use up your oxygen quickly. With a 20% oxygen, you're limited. They say it's impossible. These reptiles couldn't be this aggressive and this fast. And they realized that the reptiles had stored hydrogen peroxide in their blood, and they used hydrogen peroxide for their energy. So they could get bursts of energy. Now, that's not unusual because a lot of insects make hydrogen peroxide and spray it out. They generate hydrogen peroxide, and then when they're attacked like a stink bug, they'll spray out the hydrogen peroxide, and it's nasty. They use it. In fact, as the hydrogen peroxide decomposes, it produces a gas so they can shoot the stuff out. So to save themselves, they ended up spraying the area around them with a catalyst. So the reptiles, as soon as they attacked them, would explode because the hydrogen peroxide was the catalyst that used up all of their hydrogen peroxide immediately. Okay, that was my science fiction story for the day. How about some questions on anybody? Generally, and we finished the disproportionation, which was the hydrogen peroxide. We talked about catalysts, concentration. Oh, let's flip back to here. Lab. Remember, I started at the very beginning, bleach and my blue dye. This is what the bleach looked like. The blue dye looked like ahead of time. Here it is, it's reacted with the bleach. How can I figure out what device would I have used to find out about concentration and that reaction?
A spectrometer, right?
Right. You see how deep the blue was, and from the depth of blue, you could find out how much light it absorbed, its concentration. And we could plotted this thing and done another graph. And that's, I mean, that'd be nice. It's not as spectacular as collecting bubbles in a graduate cylinder and then using a splint with them, but it's sort of the standard method for finding concentrations now. So, okay, here we are. Oh, we're 2 minutes past. So any questions? No.
Question about solubility, but that's not quite relevant. So if anyone else has other questions, I'll wait.
Okay. Okay, looks like nobody else. Everybody's being shy. They're like me in a classroom, not saying anything, just sitting in back and enjoying things. And
in that case,
yes, okay.
When you see KSP on a quiz, I was taking a practice quiz yesterday, and I got stumped by a question with KSP. A higher KSP means more solubility, right?
A larger value, yes.
So, and then a higher concentration means it's more likely to dissolve, to precipitate.
No, to dissolve, because the concentration you're measuring is the stuff that's gone into solution. Let me flip. So I'm talking to me so you can see me wave my hands. Here we go. Yes. So the KSP is the multiplication of the concentration of the stuff that's in water. That's there. So if hardly anything dissolves in water, that multiplication is going to produce a very, very, very low value. The stuff's going to be dissolved. You won't see it unless it's got a color to it. If a lot of it dissolves, then you're going to have two larger numbers multiplying. It's the product of how much dissolves. Solubility product is the number you get when you multiply how much or the concentrations of the stuff as it dissolved. And of course, you raise it according to the equilibrium expression. So a low KSP means this stuff's not going to water. So, I mean, if you're dealing with something like lead sulfide, that's good because you don't want lead to dissolve in water. It's got a KSP of like 10 to the negative 38. But if you have something like salt, then you're going to have a KSP that might be 5, 10, 15, depending on, again, the temperature and the solubility of the material. The solubility of, darn, you can't see too well. It hasn't settled. This is still hot. Oh, you might see some of the stuff on the bottom. The solubility of calcium hydroxide.
We can't see you.
Oh, you're right. Ah, good grief. Here I am. I can see it. Why can't you? There. Here's my the calcium hydroxide. You might see there's a little bit of white stuff on the bottom, or certainly on the top. You can see the calcium hydroxide that's there. Calcium hydroxide isn't all that soluble. It's in between. I think calcium hydroxide might have a solubility product in the area of probably maybe 10 to the -2. By the way, calcium hydroxide, the white powder there, is critical. You wouldn't be able to really have nice, tasty corn without the lime that's made from calcium. There is an interesting story of enzymes and hydroxides and stuff, but that's another story. And we're past our time. Any questions or anything else that I can toss in? Because you're
Yeah, I have one last question. For absorbance, do the graphs work the same way as concentration graphs? Like when you plot the absorbance, can you infer the same things that you would about the rate being like first order, second order, and half-lives and stuff, or not really?
yes, really.
Okay.
Most
So it
definitely.
works like exactly the same.
Exactly. There's a direct relationship
Okay.
between concentration and absorbance. You know, the
Okay.
greater the absorbance, the more light that's being soaked up, the more stuff that's in there that is soaking up the light. And it's directly related, absorbance is directly proportional to the concentration. Now, there's a little tricky thing in there because there's a percent transmittance, but let's not go there because AP doesn't worry about percent transmittance. It only worries itself about.
Okay. Okay, thank
I
you.
mean, yeah, that's a long story there, and we, like I say, you don't have that much time. You got other things to study for. Okay, everybody.
Mr. Russell, I
Yes.
believe someone asked if you would be doing a session next week.
Yes. I'm not sure about yet. Right now, I've got a fun experiment that I enjoy doing. To use a joke, there'll be maybe a tie-in in it. So yes, we'll have a fun one next week. I'm not sure when. I'm sort of thinking on Wednesday, but I've got to check my calendar and see if I can get the equipment and the lab setup. This is a new lab setup. I'm going to improve it a little bit, but I think this is the one I'm going to use in the future.
Yeah. You should give us an AP pep talk before.
If you look at the discussion group, there's a clip from Ted Lasso. And after seeing that, it says, I can't give a pep talk after listening to that. And I have sort of one of the concerns is that there's so much pressure on taking the exam. And I almost wish that they would abandon the exam and not give the exam at all this year. Just say, hey, folks, you've learned AP chemistry. That's going to be the big difference. When you're in college, no one's going to ask you what your AP score was. They're not going to care. They just want to, they'll be asking you questions. You know, how do I figure out this KSP problem? And you'll be the tutor telling them because you figured it all out. And you even know about flame tests now. Not flame test, the splint test for hydrogen, which produces that bark. It's a classic bark. When you, I'll do it again on my next demo. When you put that splint in there and it's in a test tube, it goes, burp, and that's for hydrogen. If the splint bursts into flame, it doesn't pop, then you know you have oxygen. I did this experiment once using heavy hydrogen. I managed to get a hold of some heavy hydrogen. Don't ask me how, but I knew somebody on the Manhattan Project. And the bark from heavy hydrogen is a lower octave than the bark from regular hydrogen, which very, very few people know. Okay, well, that's it, everybody. Thanks for sticking around. And I hope things go well for you. And I'll try and give a pep talk. Okay, I will. But again, after seeing Ted Lasso, I'm not sure I can do it. Well, I'll do my best. Okay, everybody. Thanks for stopping by.
Bye. Thank you.
You're welcome.